This is the solution to question 9.7 in the FEEG1003 thermofluid workbook. 9.7 from the updated question numbers from academic year 2015-16. So I've drawn out the problem here as described in the question. One last thing. So we have a duct that tapers from the inlet to the outlet. We're given the diameters at each end of this circular duct, and we're told that air is passing through. We also have a water-filled manometer that measures the difference in pressure or the imbalance in pressure from the inlet to the outlet. And we're given the fluid height within that manometer. So the first thing we can do is to work out the pressure difference between the inlet at point 1 and the outlet at point 2. So from your hydrostatics, we know that delta P, so the change in pressure, equals rho GH, or rho GZ. We're given H here, 0.03 meters. It's water-filled, remember? So we're just applying this to the manometer now. So delta P equals 0.03 meters times rho G. Yeah, so 9,810. So that means that difference in pressure (294.3 newtons per meter squared). Right, so that's the first easy step. So we worked out the differential pressure. Next thing we need to do is apply Bernoulli to this problem. So we're assuming it's an inviscid flow, so mechanical energy is conserved. So we write out the Bernoulli equation for this problem. Excuse the quality university pens. But, now you'll notice there's no potential energy terms. There's nothing to suggest this duct is inclined. So we're going to apply Bernoulli along the centre line. So once there and once here. And again, from conservation of mechanical energy, you should realise that the pressure here is high and the velocity term is slightly lower, and the inverse is here. Higher kinetic energy term, so the pressure is lower in this faster moving fluid. Okay, and that's how we conserve mechanical energy. Right, so we can rearrange this and express this as P1 minus P2, which we know. But we're left with two unknowns, U1 and U2, and the question asks you to find these. So it's a given that we've got a couple of unknowns here. Now, remember, this usually comes in handy. So the principle of continuity, Q equals UA. We don't know what Q is at the moment. We've got the A at either end, we have both diameters. We have no idea what U is. Okay, so we can't quickly apply this to work out one of the velocities and then work out the other one. The question is not that quick to do. So what I want you to do now is, if you know how to solve this, carry on. If not, have a quick think about how you can use this expression and make a substitution into here, so that we're left with just one unknown rather than two, and then we can solve it. So pause the recording and have a think. And when you unpause it, I'll go through the next step that we need to do. Right. Remember, it's a fixed volumetric flow rate. So Q is expressed in meters cubed per second here. So Q is a constant equal to U1 A1 equals U2 A2. Also equals, if we expand this out, U1 D1 over 2 squared times pi. And the same on the other side. Okay. The 2 pi terms cancel. So what we can now do, we can express one velocity in terms of the other. And that's very handy, so that means that we'll end up, when we rearrange Bernoulli, with a neat equation that leaves us with just one unknown. So what we're going to do in this case is write the following. So U2 is U1 D1 over D2 all squared. Okay, and that's what we're going to use and substitute into the Bernoulli equation. So I'll make some space on the board, but whilst I do that, pause the recording and have a go yourself with substituting this into this and rearranging to solve. So you've got P1 minus P2 on one side of the expression, and then it equals some product or some form of the two kinetic terms on this side. Right, welcome back. So I've rearranged Bernoulli now. So I've got this P1 minus P2, which we've got a known value for, and rearrange the other side of the Bernoulli equation. So this is the expression that we're going to substitute in. So we expressed U2 in terms of U1. You plug in the diameter values here and work this out. You get the value of U2 is 1.56 times U1. As the diameter here is smaller, the area is smaller, that's the kind of number that we'd expect. Obviously, if you get a number less than 1, then you've done something wrong. So once again, you can have a good idea if you make a fundamental mistake. Sometimes you can tell from your answer if you've got it correct or not. Okay, so on this side we have, we'll put the numbers in now. So 294.3, half row. Remember that we're applying Bernoulli in the duct, so it's the density of the air now that we're considering. Don't get caught out by using the density of water for the manometer. And then we can expand this out. So this is equal to 1.56 minus 1 times U1 squared. Only one unknown now in this expression. Rearrange, square roots, and you find that U1 equals the answer in the book, which is 18.22 meters per second. And then from here we know that U2 equals this value times 1.56. So U2 equals 28.47 meters per second. So quite a neat compact problem, not too difficult to solve. You just need to, again, use the algebraic trick of expressing one velocity in terms of another. You've probably done it many times before on this module and in your maths course as well. So to leave us with Bernoulli with just one unknown. Again, don't get the water and the air, the densities mixed up here. One is to work out differential pressure, one is actually within the Bernoulli equation. And that's it really. Of course, you need to know this trick as well. In the Bernoulli, conservation momentum and continuity are inextricably linked, so quite often you'll have to apply more than one of those in any particular problem. Okay, that's 9.7 done.